Well, I'm tired of laying down law. You don't care to listen, you don't care at all, and you don't understand as to what it means to be with a man like me, yeah. Treat me kind, with love all the time, and tell me for what you need, yeah. The first time I trouble, you're gone to the devil, and I don't mean to burst your bubble, but I love you, and now I'm gonna miss you, and bye-bye. And I'm tired of breaking down the wall. You just keep your distance, and you don't care to call, and you don't understand as to what it means to be with a man like me, yeah. Treat me kind, with love all the time, and tell me for what you need, yeah. First time I trouble, you're gone to the devil, and I don't mean to burst your bubble, but I love you, and now I'm gonna miss you, and bye-bye. Come on, boy! And I'm tired of waiting for the fall, and you make no commitments, you can't have it all, and you don't understand as to what it means to be with a man like me, yeah. Treat me kind, with love all the time, and tell me what you need, yeah. First time I trouble, you're gone from the devil, and I don't mean to burst your bubble, but I love you, and now I'm gonna miss you, and bye-bye. Take it home, boys! Come on! And I'm tired.
All right, so last time we were talking about wrapping it up with deletion in a binary search tree. We discussed what happens when it's a leaf node, right? So for example, if you are deleting 48, right, there's no problem in just severing this connection with its parent and it goes away. But on the other hand, what happens when you want to delete, say, 60? Right? In which case it has one child only. So what we can do then is we can take this subtree here and basically promote it up here. Right? In other words, if you just look at these three nodes by itself, right, that's a linked list. And all you need to do is sever the connection both ways and then circumvent the connection here. Right? And so it works with if it's 0 children, if it's a leaf, if it's one child, right? But what happens when there's 2 children? For example, what if I wanted to delete, say, 50 here? And suppose again that there is a value hanging off over here, say 55. There we go. Well, if I tried to promote up 60 up top, then 60 would end up with 1, 2, 3 children, which is definitely not a binary search tree. It's not even a binary tree anymore. So what is the solution here? What value, again, could we go ahead and take from this and promote it up to the top? 49. Why is that? In general, what property does 49 have that means that the binary search tree property is satisfied? not the heat property, but
Like balance on the sides.
it's the maximum, right? It's the maximum among all of these, right? And so what I wanted to do, and again, we reasoned that can you have a right child if you are the maximum? Nope, that would be greater than 49, and therefore that was not the maximum. What I wanted to do before we moved on to heaps was just take a look and see what this looks like, okay? For example, we're not going to do all three of them, but we will do a couple of exercises here. For example, let's go ahead and say public T remove element T key. Right, there we go. All right, so it's kind of like find, but what we're going to be doing here is we're going to remove the element that matches the given key. All right. Removes and returns. Right. So the first step here is going to be to what? Find it. At this point, I now have find it code here in the find method. I've got find it code here in the add method because I need to find where it should be, and if it's a duplicate, reject it. Otherwise, if it's not a duplicate, then I need to add it as a new leaf. So at this point, I'm thinking I want to redo this entirely because I don't want the same code in 3 places. And so we'll think about how, actually, let's just do that at least a little bit here. Right, so for example, let's go ahead and have public tree node key get node, or find node, let's say, find node. And we'll have T key here. So I could go ahead and take this and move it down here. Right? And I will start at the root, right? And I will compare left or right. And once I find what I'm looking for, instead of returning that element, what am I going to return? I'm going to return the tree node that I found it at. If I get down to the bottom here of the tree and I don't find what I'm looking for, then I can just return null. Now my first question is, should I make this into a public method? Remember, did we do this? We did something like this with linked lists, right? Where I realized, oh, you know what? This is the same operation over and over again. Find node, find node. And so what I did is I put that into a nice convenience function because I was going to use that over and over again. But I made it private. Should I allow access to the outside world, to the actual way, internal workings of this tree node right here? Should I allow you? No. I'm going to keep that private. Because I don't want, what did we call that again? A leaky abstraction. It leaks information out to the outside world. Now what I can do up here is just simply find the node, right? Tree node key is equal to this dot find node, right, of the key. And if, x, right, give it a name, if that's null, then there's no such thing as that element, so I'll return null. Otherwise, I will go ahead and return the element in that node. Return x dot get element. There. Why are you wrong? Find node. There we go. And now I've got this in one place. And this is super convenient now because now what I can do is, as a first step here, I need to find it. Right? Find node. In fact, I'm just going to steal this code up here. Find it. There, I found it. If it did not exist, can I remove it? No. Nope. So I'm already taking care of a corner case here. If that doesn't exist, then I'll go ahead and return null, right? And be done with it. Okay? Once I've found it, though, now I need to do one of several things. Well, 2 here. Consider any other corner cases. Right? For example, what's one corner case that you might want to think about here? What if it's up here? What's the corner case that we had to think about when we added something? An empty tree. What happens when we end up emptying the tree, right? In other words, the thing you're trying to delete is the single root node. We probably need to do something about that, right? So for example, if it's not null, else if this dot size is equal to 1, right? That means that you are trying to delete the only thing in it. And so we can say this dot root is equal to null, and make sure that you're resetting your size. This dot size minus minus. So there's one corner case. I'm going to just put this as another to-do here. Consider any other corner cases, right? But that's certainly one corner case, right? And I will return here, okay? Otherwise, oh, and what do I return? No, yeah, x dot, no, I am removing the root element, and x happened to be the root element, so I will get the element out of that node there, right? Remember that we're removing and returning this, okay? Down here, what I'll do is I'll return null and also to do the rest of them. What I want to do, I don't want to do all of it because I don't want to, have a complete implementation here. That's what your lab is for. I think we give this something like this to you in your lab. But in any case, let's go ahead and do the one that's easiest. If we were to delete a leaf node, for example, let's go ahead and delete 75 in our example. Right? So I'll take care of that case right here. To do, consider any other corner cases here. I'm going to put that up at the top. Right? Else if, right? So this, or not this, but x dot is leaf. Hey, those convenience functions that I wrote a while ago are now coming in handy, right? Because if I'm a leaf, I know how to delete myself, right? All I need to do is look at my parent, right? And my parent, I need to delete my left child, at least in this case. What if instead we were deleting 85? I would need to look to my parent and I would need to delete my right child instead. So I need to determine which one am I, right? Am I a left child or am I a right child? Right? So the first thing I'm going to do is get the parent, x dot get parent. Right? And if that's not equal to null, right? If x dot parent is not equal to null, that means I have a parent. Otherwise, if I don't have a parent, then I don't. I can't ask the question of if I'm a left child or a right child, right? And x dot get parent dot get left child dot get element is equal to the key element, right? That's the logic there. Of course, it's not going to. This is not correct here. We're going to have to figure this out here, right? So follow this line of chaining. This is called chaining. When it's kind of what's called a fluent design pattern. This is not a fluent design pattern, but it's kind of like it, where you chain things together. I want to get my parent, then I want to get its left child, and I want to figure out, and then I want to get the element out of that, and I want to figure out if that's me or not, right? So did I give you that riddle? So there's this guy that's standing in front of a portrait, and he looks at him at the portrait and says, "I know this person. Brothers and sisters, I have none, but this man's father is my father's son." Who's in the picture? It's himself, right? All right. Did I do this before? No. No? All right. So brothers and sisters, I have none. So no brothers, no sisters, but this man's father is my father's son. So who am I? I am me, right? Or what's in that picture? The guy that's looking at the picture. It's a self-portrait. Right? So what are we doing here? Brothers and sisters, maybe I have one, but my parents, this man's father is my father's son. Is that me or not? Right? That's what this is doing. And I'm not going to ask using this equals equals. I'm going to ask using the comparator. This dot cmp dot compare. Right? And I'm going to compare x's element to the key that I was given. And if that is equal to 0, then that's me. I am a left child, right? X is the left child. Else, there's only one other possibility. X is the right child. There we go. Well, no, x dot get parent is not null, and so x's parent's left child element is equal to the key. Right? So I'm the left child or I'm the right child. Now let's come over here and understand what we do in that case. Now again, if I'm the left child, then I set my parent's left child to null. So my parent, x dot get parent, dot set left child to nothing. I've severed that connection. Otherwise, I do x dot get parent dot set right child to null, because that's me. And then if I want to sever the connection to my parent too, what I would do is I would say x dot set parent to null. Right? Since it's a two-way relationship, then I'm getting rid of that. Right? In any case, this dot size minus minus and return x dot get element. This is going to be repeated code here and here, right? So I probably want to take care of that later on. So else if x has one child, to do. Right? Else if x has two children, right? To do. Now I will translate these two because I want this to actually compile and we want to test this. But how do I know if x has one child? X dot get num children. This is coming in real handy now. Right? If you have two children, to do, right? And the rest of them here. So I'm going to leave those there, and I'm going to come over here to the demo. And instead of that binary search tree, we'll go ahead and keep this for a second here. No, we don't need that anymore. I already showed that. Tree utils dot large binary search tree. Right? And what I want to do is I want to go tree dot remove, like we did over here, 75. Okay, 75. And I don't care about returning it or not. And then I want to print it out as a Tixie picture, because I've got Tixie set over here to actually look and see what it looks like. There we go. Is 75 gone? There's the original. Right? And there, now it's gone. Now that worked for a left child. I wonder if it worked for a right child. Let's go ahead and delete 85 now. 85. Oops, 85. And let's run that. Return value tree node left child is null. Okay. Back to the drawing board here. That's what it looks like here. Once I have removed 75, do I have a left child of 80 anymore to find? So when I've got 85 and I ask my parent, your left child, is that me or not? Right? Then what happens? We have a null pointer exception. Let's go ahead and jump to that location there to show you what I mean here. So I am definitely a leaf, right? 85 is definitely a leaf. But when I go to my parent and I ask, am I your left child? There is no left child to compare there. Right? So I need to know, is my parent not null, and is my parent's left child not null, right? And x dot get parent dot get left child is not equal to null. There we go. So lots of checks here because there are lots of corner cases. And this is only the tip of the iceberg. I'm sure that you'd have to find a couple more corner cases as you test this entire thing fully, right? But otherwise, let's go ahead and run this and see if it works now. At least it runs. Right? And let's go ahead and put this over here. There, save, run it. And now 85 is gone now too. So 75, 85 are gone. Let's check and see if it works for 80 now. Right. Run this. Okay. Hey, it still works. Right? And the way that I would go about testing this is actually I would go into a for loop here and just start deleting everything. And as things become leaves, then I would delete them next. So I would delete 95, 90, 60, 12, 2, 15, 28, 80, 48. In fact, I would probably just go in the reverse order that I inserted them in to get this topology here. Right? But otherwise, we're definitely not done here. right? We've still got 2 more cases and probably other corner cases to deal with as well. I'll leave that as an exercise though. Because what we were looking at last time was the fact that you do not have a guarantee on the depth of that tree, right? We talked about the hill. Did we talk about it, right? And that there are balanced binary search trees, but we're not going to look at balanced binary search trees. Instead, we're going to be looking at heaps. Right? So here's my min heap again. All right, so what were the properties here that we observed last time? Right? The properties of a heap are going to be, nope, that's not what I wanted. Sorry, just a second here. Huh. Thought it was here, but okay. Try here instead. All right, here we go. All right. A heap is not a balanced binary search tree, right? Balanced binary search trees are a thing. There are dozens of them, and you might see one eventually in, say, Computer Science 3 if you end up taking that. In fact, just as out of interest here, what are you taking next fall for computing? Anybody know? Embedded systems, that makes sense. Circuits, that's EE, yeah. Data structures, what number is that? Yeah, let me know later on. In any case, there's a guarantee in the depth that is logarithmic for a balanced binary search tree, but this is not a binary search tree, but this is a heap. A heap has a fullness property that does give you the guarantee that it's going to be logarithmic depth, right? And again, the fullness property is that every node at every level is present except for possibly the last one, but that's full to the left, okay? And then you also have the heap property. Tell me about that, tell me about this key right here. It is less than both of its children. That's true for every key. 55 is less than 72 and 70. 60 is less than 92 and 63, et cetera, right? So that's the heap property. And this is the min heap property. You can go ahead and flip that because if you want to, because you can have a max heap where now the key is greater than both of its children. It doesn't really matter because in practice you're going to be using a comparator. And if you want a max heap, all you have to do is take your comparator and reverse it. And then you've got a max heap automatically. So it's not that big of a deal. The fullness property guarantees that it's going to be logarithmic. Another observation here is that the minimum element is always where? At the root. Cool. So we're always able to get this guy right here. It, however, is not a general purpose data structure. Do you remember when we looked at stacks and queues? They were only efficient because we restricted what you could do with them. We didn't let you take out a random dish from the middle or the bottom or something. We only allowed you to push and pop from one end or offer and pull from the other end. But that restriction made everything efficient. This restriction is always also going to make it efficient. I'm only going to allow you to do 2 things with this. Get and remove the minimum element and add element. And both of them are going to be order D, order depth, and because of the fullness property, you have a guarantee that both of these are logarithmic. Right? So how do you add an element? Well, we're going to always insert an element as the last element. So let's come over here and let's insert, I don't know, say 10. 10's not in here already. So let's insert add 10. Now, if I treated this like a binary search tree, I would get into trouble almost immediately. Because do I go up to right here? Well, do I go left or right? Well, 10 is greater than 5, so maybe I go right, or something. Right? Whatever criteria you can come up with, I can come up with a counterexample where it doesn't work. Right? But otherwise, okay, so I went to the minimum. I'll go to the minimum over here. I'll go to the minimum over here. And 10 is less than 45, so if I put it over here, now there's a huge gap. That's not going to be an option. Right? Instead, what I'm going to do is I'm going to start by adding it as the new last element, preserving that fullness property. Remember, the fullness property is that everything is there except for possibly the last level, and everything is full to the right. So I have to put this all the way to the left, all the way to the left. I have to put this all the way to the left in order to preserve that fullness property. Now the problem is the heap property satisfied here? Nope. So let's fix it. And that's called heapification or heapify or fix heap or something. Right? I'm going to compare it with its parent. And I'm going to see that they're out of order. So I'm going to swap them. And when I do that, 10 comes down here, or 53 comes down there. Right? So 53 is now there, and 10 is now there. Is the heap property satisfied now with respect to its parent? Nope. So let's go ahead and update that again. Right? 10 will come up here, and now 50 is down there. I'll go ahead and erase that and put in 50. Right? Is the heap property now satisfied? Yep. Do I have to worry about the other child over there? Right? 50 was up here originally, and I'm putting something in there that is no bigger than 50. So the heap property will be even more satisfied, if you want to look at it that way. And so I never need to look down to the other child over there. Right? And the heap property is satisfied with only 1, 2, 3 comparisons. Right? In the worst case, if I were to insert 0, I would have to heapify it all the way to the top. Right? But no matter what, I am going to start at the bottom and then heapify it up. Okay? That's why it's order D. Now what about get and remove the minimum? In fact, actually, let's go ahead and document this before we move on. I'm going to heapify it. I'm going to compare it with its parent element and swap it if it's out of order until either the heap property is satisfied and you can stop, you got lucky, or it becomes the new root, in which case you've gone all the way to the top. No matter what, that's going to be order D comparisons at most, assuming that you can jump to the last element. And that is actually a big assumption. How was I able to jump to that last element in order to insert that value? If I were to represent this as a tree, and I only have access to the root, do I know that the next available slot is right there? There is a way that you can figure it out using some basic mathematics and series stuff. If you're interested in that, go ahead and read the book, because I have a full write-up of it. But otherwise, I'll show you an even better way of doing this that's even more efficient. Okay? Otherwise, what about get and remove the minimum element? So the first thing I'm going to do is I'm going to save it off. There's 1. Here's my temporary variable. Temp is equal to 1. Right? All I did was take it out and put it over here, and I'm going to eventually return it. But unfortunately, I've got now a gap. Right? How do I fix that gap? Well, do I just start shuffling things up? If I did, then the minimum would come up here, the minimum would come up here, the minimum would come up here, and then I would be left with a gap right here instead. Nope. I'm going to preserve that fullness property first. I'm going to take the last element and I'm going to move it to the top. There we go. 63. That effectively removes this element down here. It's gone now. Fullness property is satisfied, right? But is the heap property satisfied? No. So once again, the same trick. I'm going to exchange it, swap it with the minimum element of its 2 children. So this becomes 5, this becomes 63. Is the heap property satisfied now? Nope. It's what I need to do is I need to compare it to both of its children. Is it less than both of its children? No. Then promote the minimum. And this becomes 50, and this becomes 63. Is the heap property satisfied now? Nope, because it's greater than both of its children. So I swap it with its minimum, 63. The only difference here is that you need to make 2 comparisons. Am I less than both of my children? And if I'm not, then I need to find the minimum among those two. And whichever one is minimum, that's the one I swap it with. And then I proceed downward to make sure that everything else is fixed downward. Again, order D. So, remove and return the element. Again, save it off so that you can actually return it in a temporary variable. Replace the root element with the last element, and once again, that's going to be an assumption that you can jump to that last element for free, right, or very efficiently. Then we heapify downward. We swap with this element with the min child until the heap property is satisfied, or you reach the bottom of the tree. No matter what, that's going to be order D. What I want to show you are two more things here. First of all, what about an implementation? Right? A tree representation is possible, but finding the last element or the next available slot is order D, which once again is order log n. Right? Instead, consider the following. What I'm going to do is I'm going to take this heap and I'm going to do a breadth first search on it. Okay? A breadth first search would start at the top and read left to right, top to bottom. 1, 5, 30, 50, 55, 40, 80, 60, 53, 72, and 70. ... I've run out of room here, but that's okay. No, that's not what I wanted. There. I'm going to put this into a data structure that you are well familiar with now after a year of computing. If I label them, it'll be abundantly clear what this is. What is this thing? What if I started out at 0? Or at 0, and then this is just empty here. This is an array. Right? All right, well, how does this help us? Let's go ahead and focus on one value here, 55. Right? So the value 55, it's at index, where? Right here. So let's highlight that. It's at index 5. Where's its parent? Where's its left child? And where's its right child? What indices? So its parent 5 is at index 2. Its left child 72 is at index 10. And its right child is at index 11. All right? Let's see if we can find a pattern here. What about its parent 5? So 5. It is at index, like you said already, 2. Where's its parent? 5 has a parent of 1, so it's at index 1. It's left and it's right. Where's its left child? 50 is at index 4. And its right child, which we've already seen, 55, is at index 5. So do you see a pattern here? If I have a node U at index, say, I, where is its parent? Where is its left, if it exists, of course? And where is its right? Left and right. So if I have an index 5 here, I see that the left is at 10. If I have an index 2, I see that the left is at 4. What do you think? 2i. 2i and 2i plus 1. Right. What about reversing that? What about going from index 5 to its parent 2 and going from index 2 up to index 1? So if I multiply by 2, then I divide by 2. But be careful. Its parent is at I divided by 2. Right. What happens when you have 5 divided by 2? 2.5. Is that an index you've ever heard of? So what do we end up doing with it? Truncating it, or mathematically, that means taking the floor. This works out if you don't burn this one. It's just that you're going to be off by one, and you need to, fix it, right? And so this is a wonderful implementation, an index-based implementation, where all you have to do to keep track of something is the index, and then you can jump immediately to its parent. You can jump immediately to its left child and right child, and you can traverse throughout this tree just by jumping to indices, by doubling it and adding one, or by dividing it by 2 and then taking the floor. This is wonderful. Why didn't we do this before? In fact, I had a student one time come back from a Google interview, and they didn't know the answer to this question either, because the Google interview asked them, why don't we always just use index representations for big giant trees? Right? Okay. Do you remember this example? 10, 20, 30, 40, ... 100. That unbalanced binary search tree, right? How big would you have to make that tree in order to store just 10 elements here? There's 10 elements here, but how big would your array need to be in order to represent this? Remember, these are all right children. So this is at index, say, 1. This is at index 2 plus 1, right? Because the right child is at 2i plus 1. This is going to be, so 3. 6 plus 1, 7, right? 14 plus 1, 15. Right? I'm going up by powers of 2 here. Eventually, this is going to be 2 to the 9th minus 1. How big is 2 to the 9th? Or actually, is this 2 to the 10th or something? 2 to the 10th, something like that, I don't know. 9 or 10. That's not a huge amount, right? This is only 1,024, so minus 1 is 1,023. 1,023 sized array in order to hold only 10 elements. It's not huge, but imagine it's not 10 elements. Imagine it's 100 elements. And they're all going down this direction. How big is it now? 2 to the 100 minus 1. Do you have that much memory in your computer? Do you have that many atoms in the known universe? Here, let me bump it up one more. Right? 1,000 elements. No, there are not that many atoms in the known universe. You can't build a computer that size. You certainly cannot hold enough information and represent an array that size. So yes, this is a great implementation, assuming everything is full, because the fullness means that there are no gaps here. What would this actually look like if you did this? You'd have one element and then you'd have this gap. You'd have another element and then you'd have a gap twice the size. Then you'd have another element with another gap that was twice that size, right? All these gaps here are exponentially increasing. And that's why you don't use an array to represent a binary tree, unless it's full, like a heap is. Okay? All right, so the last two things that I want to cover today are the applications of this. Right? So one application is a priority queue. Right? So let's come back over here and visualize this. So first of all, what is a queue? Well, a queue looks something like this, right? And we've got, I don't know, 1, 10, 5, 7, 3, 4, 9, 12. Right? Now, normally a queue is a first in, first out, and we're all very fair about it. Right? But a priority queue is not fair. Some things are more important than others. So the first thing to come out of this is going to have the highest priority. The lowest value, the highest value, it depends on how you want to look at it. We're going to look at this as the lowest number has the highest priority. Now, we're not going to replace this with 10 because 10 is the next in line. Instead, what we're going to say, Okay, now we're serving number 1. Whoever's next in line, go ahead and come to the head of the line. Well, who's next in line? 3. And they jump up to the head of the line. Right? Oh, no?
You can't cut.
Yep, well, there are cuts here because, I don't know, they paid 3 times as much or something for their Disneyland ticket ride, right? Right? All right, so that's why you don't get a Disneyland. You go to something even better.
Or you
I
just
don't
have a
know.
lot of-
Worlds of Fun or something. Right?
Just bring a lot of money and buy the fast pass.
Now, do we care about what happens when somebody with a very low or very high priority comes in? They just go wherever, right? It doesn't really matter. Right? They could go there, they could go there. What doesn't matter because whoever we're going to call next is going to have the highest priority. This is a perfect implementation over here. Why? Because the next guy in line is always at the top. We can get and remove that guy, and he's replaced with the next person in line. We can just go ahead and throw something on top of the heap, and they might end up somewhere in line down here or all the way down at the bottom or somewhere in line. We don't care where they end up because we're always going to be calling the next person with the highest priority. And so a perfect application of this is a priority queue. Right? It allows order log n operations. We don't need a binary search tree for that kind of application because we're not going to be doing arbitrary searches or deletions or insertions. We're just going to be doing these 2 operations. And this restricted access data structure is a great way to do that. Another application is what we're going to be ending on, right? The course on, because it comes back full circle to day 1. Day 1, I gave you a quote by Eric S. Raymond that said that smart data structures and dumb code are a lot better than the other way around, right? Meaning that, yeah, you can go through a coding boot camp or whatever, right? But being able to recognize when to use a data structure and when not to use a data structure and when to use a different data structure and why, that's the difference between somebody who's studied computing and somebody who's just gone through a boot camp, right? So let's take a look at the quintessential example of this. Actually, let's go back over here first, all right, and erase all this. There we go. All right, so if I started taking things out of this heap, what would I end up taking out first? 1. What would come back up here? 5. Right? Okay, maybe something else, I don't know. But the next thing to come out of it would be 5. What would come out of it next? 30, all right. What would come out of it next? 40, all right. What would come out next? 45, it looks like, I think. Then 50, then 53, 55. Did I get them all? Right? Then 60, 63, 65, et cetera, et cetera. Tell me about this. It's sorted. It's in order. That is heap sort. Oops. Heap sort. So the usual input and output. My input is going to be a collection. A, having A1, A2, AN. Right? And my output here is going to be A sorted. Okay? All I need to do is create a new min heap. And then for each element in my input, just put it into this heap. For each A in A, H dot insert A. That's it. Now I need to pull them out, right? For I running from 1 up to n, what I'll do is I'll output H dot get min, with the understanding is that that's get and remove min. Tell me about that code. This is dumb code. Dumb as in it's straightforward, simple. You put stuff in, you take stuff out. You put stuff in, you take stuff out. That's it, right? Tell me about this data structure. Smart data structure. Now, what's the other way around? What's the no data structure or dumb data structure? Quicksort, or merge sort, or tim sort. Dumb data structure. What data structure did we use there? An array. It just holds stuff. There's no bells and whistles to it at all. Right? So clever code. I'm not even going to say smart code. I'm just going to say it's clever code. But it uses recursion. It uses this really cool in-place partitioning thing of its quicksort, right? And then it makes a recursive call, right? Clever code, dumb data structure, right? Which one is better? Put stuff in, take stuff out, versus all that. Right? So think back to your lab 13. If I had just given you pseudocode and had you do a quicksort or insertion sort, right? You could have probably have, translated that. But if I just described the algorithm to you, how difficult would it be to come up with that clever code on your own? Pretty damn difficult. What about this and this? Anybody can do that. Right? This is much more maintainable. This is much more clever because you're using a smart data structure. Now, is it smart enough that it's going to beat quicksort over here, which is order n log n? Because we're kind of sunk if this is all inefficient. So let's go ahead and reason about this. In other words, let's analyze this. So insertion phase. Each one of those iterations has a label. Here's the first iteration, second, third, fourth, ... Let's keep track of the size of the heap, H. Now on iteration 1, the size is 0 because you haven't put anything into that heap yet. After that, you have 1 element in the heap. After inserting 2 elements in the heap, 3 elements in the heap, etc. ... The last iteration is iteration n, in which case the number of elements in the heap is n minus 1 because you're going to put in the last element, and now it's got n elements. Right? What is the complexity of insert? Remember that it's going to be order log n. But now n is the size of h. Okay? So over here it's going to be log of 0. Careful, we'll come back to that. Log of 1, log of 2, log of 3, ... log of n minus 1. Okay? Well, first of all, log of 0, is that defined? Nope. So we'll re-reason about this. If I'm going to insert something into an initially empty heap, there's no comparisons at all. So this is actually 0. If I'm going to insert something into a heap of size 1, technically it's not 0, it's plus 1, plus 1, plus 1, plus 1. I don't want to have to worry about those plus 1s though. So what I'm going to do is I'm going to go ahead and just ignore them. Okay? Now what is the total complexity here? If I were to sum all of these up, again, I'm going to ignore this one right here. I'm going to focus on these right here. Now it's time for some math. Log of 1 plus log of 2 plus log of 3 plus ... plus log of n minus 1. Right. Log identities. Log of A plus log of B is equal to log of A plus log of B.
Oh, wow.
Log of AB. Do that 1, 2, 3, ... n minus 1 times. And this is equal to what? Log of 1 times 2 times 3, ... times n minus 1. Okay? Tell me about that.
It's factorial.
That's a factorial, isn't it? Right? So this thing right here is going to be n minus 1 factorial. Right? Or the gamma function, if you've heard it called that before, right? What I want to do is I just want to establish a big O analysis of this. So I'm going to be a little bit loose about this. This is less than or equal to log. What's bigger than n minus 1? That's a little bit more clean. N. What's bigger than n minus 2? Well, n minus 1, and yeah, let's make it even bigger though. N times, what's bigger than 1? N is bigger than 1. What's bigger than 2? N is bigger than 2. Right? Why? Because n is greater than or equal to 1. Right? There's no point in sorting something that has 0 elements. Right? Times, times, dot, 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 times, times. Now, how many n's are here? Well, so there are n n's here. N times n times n, how many n times is going to be? Log of n to the n. One more log identity. What do I do with that exponent? Comes out front. N log n. So, did we match the complexity of quicksort? In this phase, we certainly did. This right here is going to be order n log n. Darn it, what about this phase right here? It's exactly the same, but in reverse, because you're taking it out each time. Right? This is called amortized analysis. Have you ever heard of that term before? So you take out a loan for $1,000, right? And you're going to be paying it back month. Let's say $1,200, so you pay it back $100 each month. They're charging you interest on that, but they're only charging you interest on the balance, right? In the first month, there's $1,200 there, so you're paying interest on the whole $1,200. But in the second month, you paid that down $100. You're only paying interest on $1,100. Then $1,000, $900, $800, etc. What is the actual amortized cost of that loan over the life of the loan? Right? You're not paying interest on $1,200. You're not paying like 5% on $1,200 would be $60. You'll be paying much less than $60. Right? So the true cost of the loan is not $60. It's going to be $35 or something like that. Right? The true cost of this data structure is not fixed because it's growing and then it's shrinking. Right? So over the lifetime, not of the loan, but over the lifespan of this algorithm, over the execution time of that algorithm, the cost goes up and down. But when you add up all the cost, then it becomes efficient and log n. And once again, this is going back all the way to the beginning of the semester, where smart data structures and dumb code are a lot better than the other way around. Right? So, the conclusion of the course is smiles, smile face. And this one is sad face. Maybe, oh, is red is sad face? There we go. There we go. Right. So, smart data structures, dumb code are a lot better than the other way around. That concludes all of the topics for the course that I intended to do. So next week what we're going to do is on Tuesday I'll give a course retrospective. What have we done? Where have we been? Right? And share that number with me, and I'll look it up and see what's going on there. But otherwise, Thursday of next week, then I'll still be here. We'll still have lab on both of those days. Even though your labs are done, you don't need to turn anything in. We'll still be here as basically open office hours, open help hours for, you still have your assignment 7 this Friday. You have assignment 8, which is all written for next Friday, and then you have your design document, which hopefully should be like 90% done at this point. You just have to finish it up and turn it in next Friday. Right? But otherwise, make sure that you're doing those course evaluations for the bonus too. In this week's retrospective, I'll give you updated numbers on what the completion rate is. But otherwise, I'll see you next week.
I guess I had